Welcome to my channel and thank you for watching the videos. In this video we have to find out Laurent series for two series have been given. E to the power 2z upon z minus 1 cube about z is equal to 1, and second is 1 upon z square z minus 3 whole square about z is equal to 3. This is a question of 1994 UPSC CSE Maths Optional Paper 2 CA, question number 6a. So we will do it by writing in two manners. Method is same but only writing is different. So we take z minus 1 is equal to u, and then z is equal to 1 plus u. So e to the power 2z upon z minus 1 cube will be e to the power 2 plus 2u upon u square, which is equal to e square upon u cube into e to the power 2u. So we take e square upon u cube common and we expand e to the power 2u, which is 1 plus 2u plus 2u square upon factorial 2 plus 2u cube upon factorial 3 to the power 4 upon factorial 4 and so on in bracket close. So if we multiply e square upon u cube inside and u is equal to z minus 1, this becomes e square upon z minus 1 cube plus 2e square upon z minus 1 square plus 2e square upon z minus 1 plus 4e square upon 3 plus 2e square upon 3 into z minus 1 plus so on. So z minus 1 is a pole of order 3 or triple pole. The series converges for all values of z is not equal to 1. So this is one way of writing and getting the solution. Now let's see the second, which is same method, only way of writing is different. E to the power 2z, which is in numerator of the series, is analytic and everywhere in the complex plane. This we can see with the help of Cauchy-Riemann equations. We can write down e to the power 2 into x plus iy, and then we can apply Cauchy-Riemann equations and see that they are satisfied. Therefore, this is analytic everywhere in the complex plane. I hope you can do this. Now, Taylor series of a function is that if we apply Taylor series on e to the power 2z with center z is equal to a, we can write it in summation form. Sigma n is equal to 0 to infinity dn upon dzn, because we are taking nth differentiation, and of e to the power 2z. So this is nth differentiation of e to the power 2z at z is equal to 1 upon factorial n z minus 1 to the power n. This is e to the power 2z and the function is e to the power 2z upon z minus cube. So here we can just write this term, still z minus 1 cube is not there. We differentiate it 10th times. So this becomes 2 to the power n e to the power 2z. But when we put z is equal to 1, it becomes e square upon factorial n into z minus 1 to the power n. So I hope this is clear. Only thing, we have differentiated it n times and put the value of z as 1. Now for expansion, we take the full function e to the power 2z upon z minus 1 cube. This we have taken, and from the previous slide we are writing the series which we have obtained for e to the power 2z. So in that we are multiplying it by 1 upon z minus cube. So when n is equal to 0, we get e square term and multiplied by 1 upon z minus 1 cube. When n is equal to 1, we get 2 to the power 1 e square upon z minus 1 square, because z minus 1 will cancelled out here. Next will be 2 square e square upon factorial n is now factorial 2, and z minus 1 cube and in numerator it will be z minus 1 whole square. So square will cancelled out and denominator we will have z minus 1. So we are just writing the values with the help of series which we obtained for e to the power 2z with the help of Taylor series and multiplying it by 1 upon z minus q. So the last term can be written n is equal to, now from 3 up to 2 we have taken here. So from 3 to infinity 2 to the power n e square upon factorial n z minus n minus 3, because 3 terms we have taken. So this can be just the first 3 terms are same. Last term just we rewrite sigma n is equal to 0 to infinity n plus 3 we have made, because we have made it from n is equal to 0. E square n plus 3 factorial means we are writing n is equal to n plus 3 and z minus 1 to the power n, because n is equal to n plus 3, so minus 3 will cancel out, which is the required Laurent series of the given function, that is e to the power 2z upon z minus 1 whole cube with center z is equal to 1. It is valid in the ring 1 is less than mod z less than infinity. Now let's do the second part. In this function is 1 upon z square into z minus 3 whole square, all in denominator, and z is equal to 3. So here we do as we did in the previous example, that we assume z minus 3 is equal to u, and then binomial theorem we use, which is 1 upon z square into z minus 3 square is equal to 1 upon u square into 3 plus u square, all in denominator, can be written as, we take 3 common in denominator, it becomes 1 upon 9 u square, that is 3 square u square, 9 u square, into 1 plus u upon 3 whole square. So which is equal to 1 upon 9 u square. In bracket we expand the series 1 plus u upon 3 to the power minus 2. So if we expand that, it becomes 1 plus minus 2 into u upon 3 plus minus 2 into minus 3 upon factorial 2 into u upon 3 square plus minus 2 into minus 3 into minus 4 upon factorial 3 into u upon 3 cube, and so on. So when we cancel u square and divide by 9 also, it becomes 1 upon 9u square minus 2 upon 27u plus 1 upon 27 minus 4 upon 243u plus, and so on. So we can write down it as, we substitute the value of u, it is 1 upon 9 into z minus 3 square minus 2 upon 27 into z minus 3 plus 1 upon 27 minus 4 into z minus 3 upon 243 plus so on. So z is equal to 3 is a pole of order 2 or double pole, and this series converges for all values of z such that 0 is less than mod z minus 3 is less than 3. So this we can solve by this method also, that fz we take 1 upon z square, then f dash z is minus 2 upon z cube, then f double dash, then we find out nth derivative of f, which is equal to minus 2 minus 3 and up to minus n minus 1 upon 2 upon z to the power n plus 2. So we can write down z as 3 and we get values for this. Thus the Taylor series of fz with center 3, we can write down, this is 1 upon z square we are taking. So sigma 0 to infinity minus 1 to the power n, because we have written here this term. It's alternate sign, so minus 1 to the power n, and you can see when it is first derivative it is n plus 1, so n plus 1 factorial upon 3 to the power n plus 2. N is 1 and n plus 2 is 3. So that way we have written here minus 1 to the power n plus 1 factorial 3 to the power n plus 2, and this is due to Taylor series factorial n, and this is z minus 3 to the power n. This is due to Taylor series. Nth derivative we have taken here, in that we had written the previous example, we had written dn upon dzn of e to the power 2z. So same thing here, already done the nth differentiation and kept here, which is equal to sigma n is equal to 0 to infinity minus 1 to n plus 1 factorial was there, but that has been cancelled out with n factorial, so only n plus 1 is there, upon 3 to the power n plus 2 and z minus 3 to the power n. We take full function here, which is given in second part, 1 upon z square into z minus 3 square. So 1 upon z square series we got, we multiply it by 1 upon z minus 3 whole square, we get this series. Now put n is equal to 0, we will get this term, put n is equal to 1, we get this term, and from, so we take plus sigma n is equal to 2 to infinity. So we take m is equal to n minus 2 to infinity, and we substitute minus 1 to the power n. N is equal to m plus 2. So this is m plus 2, then m plus 3 is, because in place of n we are writing m plus 2. So everywhere we are writing this and getting the expression. And this is the required Laurent series